Okay, welcome to chapter 24, probability. This video will be on the first 5 sections. Like so many other chapters in the book, I think this chapter, each section feels pretty straightforward and easy as we go through it. But by the time we're done with the entire chapter, we take a moment, step back, and reflect, we'll see that there's some really amazing ideas here and some complex concepts that we're going to need to work through. Anyhow, let's jump in. This first slide has everything you need to know from sections A and B. So this is really just some vocabulary for us. You should understand what I mean when I say the word trials, outcomes. Relative frequency, by the way, is exactly what we mean when we say experimental probability. So when we're talking about the probability of something occurring, there's two different things we might mean. One is theoretical probability, which we'll talk about that later. That's like saying, hey, when I roll a dice, there's a 1 in 6 chance of me rolling a 2. Experimental probability would be, I have a very particular dice, I roll it a million times, and what's the actual relative frequency of a 2 having been rolled? It's probably not going to be 1/6. It might be something pretty close to that. So that's what we call experimental probability, because it's a probability that has been generated from the running of experiments, which in the context of statistics is certainly not any wild scientific experiment that we do in a lab. It's just we're going to do a random process and see what happens. Below that we have the sample space. That's just a list of all the possible outcomes of the experiment. Some people would call it the universal set U, so we'll see this in some diagrams later on, in particular the Venn diagrams. And there's a lot of different ways that we could draw our sample space, and I think we'll see an example of each of these over the next couple of videos.
Some of you are surely being critical now of how I chose to pronounce the singular of the word dice a few moments ago. However, I follow proudly in the footsteps of YouTube mathematician and comedian Matt Parker, and so you'll see, through the remainder of this video series, as well as in life, Mr. Ropke never says die.
And guess what? There's no interesting problem from section A and B. We're already in section C. So now we have the theoretical probability being defined up top, P of A. And it's being defined as the number of members of the event A divided by the number of possible outcomes. Here notated as N being the number of events in A divided by the number of events in U, the universal set. So if I have 50 jelly beans in a bag, then the number of members in my sample space is 50. And if of those 50, 11 of them happen to be yellow, then the number of members in my event A being choosing a yellow jelly bean would be 11. So the probability of choosing that yellow jelly bean would be 11 out of 50. Sorry if that was obvious, but I feel like this definition is potentially confusing just due to the language in it. But I think it's something that you can all certainly grasp numerically. The theoretical probability of any event is going to be between 0 and 1 always. 1 being it's 100% definitely going to happen, 0 being 0% chance. There's no such thing as any probabilities outside of those numbers. So if in your work you find yourself getting a probability that's negative or is bigger than 1, stop. You've made an error. Go back and try again. Then 2 events will be called complementary. If exactly one of them has to happen, their probabilities together are going to add up to 1. So for the jelly bean example earlier, if there was an 11 out of 50 chance of picking a yellow jelly bean out of my bag of 50 jelly beans, then there has to be a 39 out of 50 chance of picking not a yellow jelly bean, assuming that I must be picking some jelly bean. And adding the two of those together, I get 50 out of 50, or 1. Okay, so a few moments ago, we saw 5 different ways to represent the sample space. The first was to make a list, and that's exactly what we're going to do here, to write out the 8 possible 3-child families according to the gender of the children, assuming the standard binary options. The trick with lists is to not just write down elements of the set all willy-nilly. We're going to try to do this in an orderly fashion. So the way I would do this here, where I have two different options for each of the children, is to write down, this is just going to be the first child is either a boy or a girl. I'm going to write it down 4 boys and then 4 girls, because it's half and half. We know there's 8 different possibilities here, so there we go. And then for the second child, I'm going to alternate, but this time it's going to be 2 and 2. And then the third one is going to be every other one. And that's all 8 of the possibilities. And I knew there would be only 8 options here, not only because the problem said so, but also if I think back to chapter 8 of the textbook with the counting principle, there were 3 children and each of them had 2 options. So the total number of options should be 2 times 2 times 2, 2 to the third power being 8. Now that I have them all, we can determine these probabilities just by looking at the list. The probability that it's all boys is just going to be 1 out of 8. That's the very first option in the list. All girls should also be 1 out of 8. Boy, then girl, then girl. There's only one possible way to do that. That's a very specific permutation. 2 girls and a boy. Now this one here doesn't have order, right? So that's slightly different than option 3. 2 girls and a boy, there's actually 3 of those. Now we can know that it's 3 by looking through and spotting the 3 of them. So 2 girls and a boy is here and here and here. But the fast way that I like to think about that is I just imagine, okay, if there's 1 boy, that 1 boy is either the first child or the second child or the third child. So there's 3 different places for that 1 single boy to be. Therefore, 3 out of 8 is my answer for this. That's a really helpful technique to use, especially when the sample space gets a little bit larger and we have more, I mean, it's not always going to be children, but if there were more children involved here, I would use that technique rather than try to find which one of these items actually has 2 G's and a B. Anyway, back to the problem at hand. Roman numeral 5, a girl for the eldest. That's obviously going to be 1/2. It doesn't matter whether it said eldest or youngest or middle child. That specific child, which this problem is asking about, was either a boy or a girl, so the answer has to be 1/2. And finally, Roman numeral 6, at least 1 boy. At least 1 boy means it could be 1 boy, or it could be 2 boys, or it could be 3 boys. So again, we can look through the list and we can identify each of those 7 options. So it is going to be 7 out of 8. Or we can think about the complement of that event. If there's not at least 1 boy, that means that it's all girls. I already know that all girls is 1 out of 8. So its complement, at least 1 boy, must be 7 out of 8. So now we will look at our second way to illustrate a sample space, a 2-dimensional grid. So for the 2D grid, we're going to have each axis is going to represent one of the events that is occurring. In this case, we are rolling 2 dice. So a 2-dimensional grid is only really usable when we have 2 things happening. If we had a third event, then we would need to be building a 3-dimensional lattice, and that's not particularly easy to visualize. We have other ways to deal with that. Anyway, let's use the grid below to answer this particular question. What's the probability of getting 2 3s? Well, 2 3s is just this point, right? That's terrible. You know, that one right there is the one I'm aiming for. And that's 1 event out of a grand total of, well, this grid is 6 by 6, so that's 36. So we got 1 out of 36 for that one. A 5 or a 6 or both. Well, it could be a 5 or a 6 or a 5 or a 6. Let's count all those up. It's not 24 out of 36 though, right? Because these 4 are getting counted twice. So we need to be really careful about this. So we're going to have 20 in total. This is going to be 20 out of 36. So that's a really important thing to look out for with problems featuring the word or, is that we're going to have double counting that we need to be careful of. We'll worry about that more later on when we're dealing with just probability formulas. It's pretty easy, I think, to catch that here because we have this visual where obviously we were double counting those 4 dots in the top right-hand corner. Okay, moving on. Exactly 1/6. So that's these 5 and these 5. We're going to ignore that dot in the tippity top right because that had 2 6s and we want exactly 1. So this is going to be 10 out of 36. A sum of 7. So a sum of 7 would be a 1 with a 6, or a 2 with a 5, or a 3 with a 4, or a 4 with a 3, or a 5 with a 2, or a 6 with a 1. So there they are. That's 6 out of 36. A sum of 11 or 7. So, well, I guess I shouldn't have erased those. I'm going to need those back. And then for the sums of 11, that could be a 6 with a 5 or a 5 with a 6. That could also be, I guess that's the only way I could get 11 out of these though, right? Because I can't have 4 with 7. So there you go. That's going to be 8 out of 36. If that problem had said something ridiculous, like a sum of 7 and 11, then I would have said the probability is 0. There's no way that I could have a sum of both 7 and 11 at the same time. To the right-hand column, I just realized I've been doing these letters out of order. Whatever. To get a 5 and a 6. A 5 and a 6 is going to be just those 2 particular options. So that'll be 2 out of 36. At least 1 6. That's going to be all of those. We need to be careful not to double count again. So that'll be only 11 out of 36. No 6s. By the way, no 6s is going to be the complement of what we just circled. So subtracting 11 from 36, that'll give me 25 out of 36. A sum greater than 8. If I do this carefully, there we go. Everything to the bottom left of that division is a sum that's either equal to 8 or less than it. So we're looking for the ones that are above and to the right of it. And that looks like it's going to be exactly 10 dots. 10 out of 36 will have a sum greater than 8. And then a sum of no more than 8 is the complement of that. So that will be 26 out of 36. There you go. That's a 2-dimensional grid. And we're now in section D, continuing with the illustrations of sample spaces. Here's a table of outcomes, very similar to a 2-dimensional grid, except this data is pulled from surveys or some situation in which we can break down people into various categories and then tally up how many people fall into those categories, and then we see how those categories interact with each other. So here we have children and adults, and we're assessing whether they liked or disliked some ride that they went on. Just want to point out one thing about the vocabulary of the question here. It says to use this table to estimate the probability that a randomly selected person who went on the ride exhibits one of these traits down below. And at first glance, you might be thinking, well, wait, am I estimating the probability? I mean, shouldn't I know exactly what the probability is just by looking at this number? Like, am I supposed to round that? No, that's not what it means. It's saying that we're going to estimate the probability because we're not actually surveying everybody here. It's very unlikely that this is a complete census of data of people riding the ride. This is probably just a sample of some riders. So we're going to estimate the probability that a randomly selected person from all of those who rode the ride would have liked it or not. Anyway, the trick here is to actually expand the table and give yourself more information than is immediately available to you. Like maybe get some totals. Like I would like to know the total number of adults, of children, total number of people who liked the ride and who didn't like the ride. So we're going to extend into an additional column and an additional row. There's that for you. You can always check your work. You can make sure that the total number of children and adults is equal to the total number of likes and dislikes. In this case, they're both equal to 130. And now we can assess the questions, because the probability that someone liked the ride is just going to be 83 out of 130. The probability that someone is a child and disliked the ride, those 17 people are the only ones who were children who disliked it, so that'll be 17 out of 130. Forgot to write down the first answer. Letter C, if you were an adult or you disliked the ride, that means we need to look at all of the adults. So that's our 58. But we should include the 17 children who disliked the ride. Just like with that table before, I'm not going to add up 58 with 47, because if I do that, then I would be double counting these 30 people. They'd be counted both as an adult as well as someone who disliked the ride. So I don't want to do that. So I'm just going to add up 58 plus 17. Or my other option is we could do 47 plus 28. We're going to get the same answer either way. So 75 out of 130. And this last one, very important word here. They liked the ride given that, so two very important words, given that he or she is a child. What we're going to do there is we're going to only look at children. So we're going to no longer look at the total as being 130, but we're going to consider the total to be only 72. And we're going to ask how many of them liked the ride. In this case, it's 55. So anytime we see the phrase given that, that means we're going to actually change what the denominator is of our theoretical probability fraction into whatever the number is that's attached to the phrase that comes immediately after the phrase given that. It's going to play a huge role later on in the chapter, so we will most definitely see it again. And that brings us to section E. So some more new vocabulary here. We need to discuss what independent events are. Independent events, essentially, they're independent of each other. They have no impact on each other. One's probability, or the occurrence of one, I should say, has no impact on the probability of the other's future occurrence. Multiple events can be independent of each other. It doesn't need to be only two, although most of the work that we do will focus on two events happening at a single time. If two events are not independent, they are, of course, dependent. And the important thing to take from this is when we're working out the probability of A and B both happening simultaneously, it's the probability of one multiplied by the probability of the other. All right, here's a fairly straightforward independent event problem. We have two people firing at a target at the same time, so they should be independent of each other. Whether or not Jiri hits the target should have no effect on whether or not Benita hits the target. All right, so the probability that they both hit the target. I know that Jiri hits 70% of the time. I know that Benita hits 80% of the time. We multiply those two together, and 56% of the time they will both hit the target. For them to both miss, we know that Jiri is going to miss 30%. Benita is going to miss 20%, just subtracting each of those hit percentages from 1. Multiplying those two together, we're going to get 0.06. So 6% of the time, they'll both miss. For Jiri to hit, but Benita misses, that's going to be 0.7 by 0.2. And for Benita to hit, but Jiri to miss, that's going to be 0.3 times 0.8. Multiplying those through, it's going to be 0.14 and 0.24. And if we add those four numbers together, you'll notice that they all add up to 1 because there's no other possible scenario that could occur. One of those four things is definitely going to happen. If you're a fan of more visualizations, we could have done extra work in this problem. So here's just two ways we could have done it. In red, we could have made a grid or a table. I've got Jiri on top and Benita on the left, and I've got hit or miss labeled for both of them. And then in each of the four boxes, I've written down the products that I had in green. And then in blue, I have something that we're going to cover more formally in the following video. This is a tree diagram. I chose to do Jiri first, but you could also have flipped this tree diagram around. We could have done Benita as the first step and then Jiri as the second step. You'll get the same answers either way in the end. But I've got the first branch here is when Jiri hits, so that's 0.7. And then I branch off from that. Either Benita's going to hit or Benita's going to miss. Here, Benita's going to hit or Benita's going to miss. And at the end, I have, again, 4 different outcomes, and they all add up to 1. And I want you to think back again, like through all this, go back to chapter 8, where we learned about counting, and that was the first time that we encountered the words and or. When we have an or situation, it means that we need to add things up. When we have an and situation, it means that we need to multiply together. So the very top thing here, this is Jiri hitting and Benita hitting. So we multiply together. But it could have been Jiri hitting and Benita missing. So it's Jiri hitting and Benita hitting, or Jiri hitting and Benita missing. So I've got a product plus the second product, plus this third product, plus this fourth product. And that gives me all of the possible outcomes. Anyway, moving on. We talked about independent, so dependent is obviously just the opposite of that. I mentioned this earlier. The key here is that we need to assume that one of the events has occurred to then analyze how the probability of the second one would have changed. And I'm bringing back here the definition we saw earlier for independent events. There we use just the word and, whereas here we see that we're using the word then. Now for the most part, the word then is just a fancy way to write the word and. It still means we're going to be doing multiplication. It still means that two things are both happening, but it is very helpful with dependent situations to kind of pretend that they're happening in a specific order. With independent events, it didn't matter. If we think about our sharpshooters, if we had said, okay, Jiri actually shoots first and then Benita shoots second, or vice versa, the numbers are all going to be the same. It's not going to change the values of any of our answers because they're independent of each other. So whether it was then or and, it didn't matter. However, in the problem that we're about to see, it's very important that we really do interpret the question as having a time component so that we, as I said, can analyze how the probability of one event is changing based upon the outcome of another. But actually, before we look at dependent events, I want to actually just talk a little more about and then, and go back to an earlier question about the pair of dice. Here I circled in letter B the probability of getting a 5 and a 6. And we said that the answer should be 2 out of 6. And again, that was because in our grid, there were exactly 2 options here and here, which had both a 5 and a 6. Now think about that for a moment. Rolling the 2 dice, clearly independent events. Getting a 5 has a probability of 1/6. Getting a 6 has a probability of 1/6. But 1/6 times 1/6 is equal to 1/36. So why is the answer here 2/36 if and just means we should multiply them together since they're independent? Well, the reason is that when we're getting a 5 and a 6, that's either a 5, then a 6, or a 6, then a 5. This first one gives us 1 out of 36. The second one also gives us 1 out of 36. We add them together to get 2 out of 36. So this is, I think, one of the challenges within probability is that you might have a very easy way to go about answering a problem. In this case, just by looking at a grid, the answer was obviously 2 out of 36. But if you try to think about it using some other concepts, you should still get to the right answer, but only if you really think about it hard enough. Like you've got to really understand now, what does the phrase 5 and a 6 mean? Are there different orders to it that I need to take into account? So in some problems here, we need to even start thinking about permutations and combinations from way back in chapter 8. And actually, we'll hit that at the very end of this chapter officially. But we can analyze some problems even now using that mathematics, although I think that actually makes the problem more challenging than it needs to be. But maybe it's something that you were going to naturally try to do. So I just want to mention that this is an option, either to discourage you from ever trying it or to at least encourage you to do it right if you do need to try it out. Anyway, let's move on and look at some dependent events. So, I mean, this problem here should immediately remind you of Chapter 8, combinations and permutations. And we will analyze this both different ways. So first, find the probability that 2 students will be 2 boys. The hard way, I think, is to use combinations. And the way that would look here is we have 2 girls that we could be choosing from, and I want to choose none of them. And then we'll multiply that. We've got 5 boys, and we want to choose 2 of those. But then we need to think of the total situation here. There were 7 children in total, and we're going to be choosing 2 of those. So evaluating each of these binomial coefficients, 2 choose 0 is 1, 5 choose 2 is 10, 7 choose 2 is 21. So final answer is 10 over 21. What I think is the easier way to do this is to think of it this way. The first student that we choose has got to be a boy. How many boys are there? There's 5 of them. So that first boy being chosen has a probability of 5 out of 7. Now, let's say we've chosen that first boy. When I choose the second boy, how many boys are left? Well, there's only 4 left in the group. How many people are left in the group in total? Well, only 6 now. Multiplying through, we've got 20 over 42, which is, of course, 10 over 21. So I think that's a much simpler way to do this. Let's look at the second one. So now I want it to be the eldest 2 students. Again, combinations. There are, for these 7 students, there are 2 students who are the oldest, and then there are 5 students who aren't. So out of those 2 students who are the oldest, I want to choose both of them. And then out of the 5 students who are not the oldest, I want to choose none of them. And again, we're dividing by 7 choose 2, because that's the total number of ways that I could choose these kids. Multiplying through, 2 choose 2 is 1, 5 choose 0 is 1, 7 choose 2 is still 21, so we get 1 out of 21. Doing it with just fractions directly. My first pick needs to be one of those 2 oldest children. So there are 2 of them, and there are 7 kids in total. So now I've chosen one of those 2 oldest kids. My second choice needs to be the other one. There's only one of them left, and there's 6 kids left in the group. So that's going to give us 2 out of 42, which is 1 in 21. I guess it's like a third way that you could think about this if you really wanted to. You could say, well, I'm either choosing the first oldest, then the second oldest, or the second oldest, then the first oldest. So if I'm choosing the first oldest first, there's only one who is the oldest out of 7. Then when I choose the second one, there's still only one who's the second oldest out of 6 remaining in the group. What I get there, I'm going to add to from the or. There's only one who's the second oldest in the group, if I were to choose them first, times there's still only one who's the first oldest out of the 6 who are left. So we have 1 out of 42 plus 1 out of 42, giving us 1 out of 21. So that's the end of this one. Out of the 5 different visualizations for sample spaces, we've already seen 3, 2-dimensional grids, tables of outcomes, and lists. And I guess technically I already did a tree diagram, but that's coming up in the next video. That tree diagrams have got their own section, in fact, and then Venn diagrams do as well. Tree diagrams, super, super important. Venn diagrams, they're cool, but not going to be a big deal. Later on in this chapter, we've got laws of probability, pretty important, and that's going to be a tough one for some of you. You can see we've already previewed here section K, talking about permutations and combinations, and then that's pretty much it. I mean, the end of the chapter, Bayes' theorem, sounds fancy, but it's really just a tree diagram, so whatever. All right, so I hope you enjoyed. I hope you're feeling empowered. Like, probability is not that hard. It's not a big, scary monster. You can do it too, although be forewarned, later on in this chapter, I will share with you some of my very favorite all-time probability paradoxes. These problems are designed to blow your mind as they once blew mine, but that is a conversation for another day. So until then, take it easy.